This is lecture number 19 of the course AU 203 Statistics and Quality Control. In this lecture, we will go into the normal distribution, one of the important distribution. Another name for normal distribution is the Gaussian distribution, and we will go into the probability density function for this Gaussian distribution. We will see that the mean and variance is actually representing the shape of the distribution. We will be able to calculate the probability of normal distribution from the graph as well as from the Minitab. So the Gaussian distribution is actually called as normal distribution. So it is one of the most common statistical distribution which arises in so many applications in physical sciences, biological sciences, social sciences, and in so many occasions where we are actually conducting measurement. So the shape of this distribution is a bell-shaped curve, and there are so many populations. When you talk about populations, it means it is the group of the people, it could be the group of the parts that has been produced, or it could be anything which is under study. So a lot of data is actually following this particular distribution. So according to American statistician Uden, the normal law of error stands out in the experience of mankind as one of the broadest generalization of natural philosophy. It serves as the guiding instrument in researches in the physical and social sciences and in medicine, agriculture, and engineering. It is an indispensable tool for the analysis and the interpretation of the basic data obtained by observation and experiment. So this quote of Uden covers the importance of this important distribution and this bell-shaped curve, which is representing the normal behavior. So whenever any distribution follows this curve, we consider that population to be a normal population. Okay, so as we already know that probability density function is a mathematical function, and if you provide a value of a random variable, this mathematical function gives you the probability of that random variable. So as we know, this distribution is dealing with the continuous random variable, so its probability density function is represented by a continuous curve, and the equation of the curve is f of x 1 over sigma square root of 2 pi and e to the power some minus half times x minus mu over sigma whole square. And the range of this function lies from negative infinity to plus infinity. It means x can take any value from minus infinity to plus infinity. And so if you are looking at this equation, here 2 and pi are constant, and x is a random variable where you are dealing with two parameters. Mu represents the expected value of the distribution, and sigma is its standard deviation, which is the square root of the variance. So this distribution is actually called as two parameters distribution. It is like the same as we have already seen in a discrete distribution like binomial distribution, which is involving two parameters like number of trials and the probability of success. So here the parameters are the mean and the standard deviation, and the mean is exactly the same as if where x is your random variable. As you know, the notation that lies with the x is x can take any value from minus infinity to plus infinity. So if you calculate its expected value, it would be the mean of that distribution, and obviously the value of the mean would be on a real number line, can be plotted. Similarly, if we calculate the standard deviation, it is the same definition as square root of the variance of that random variable. So if x is a continuous random variable, if you calculate the variance and take the square root, we are going to get the standard deviation of the distribution. And since variance of a random variable must be some positive value in order to have some positive real number for standard deviation, so variance would be always a positive value, so the corresponding square root of that positive value would append at the positive number, because if square root of negative becomes a complex number, so it doesn't have any meaning. So here sigma is always a positive value. So in short, we represent this normal distribution. X is a random variable and n represents that it is normally distributed, and we represent this distribution by signifying the mean value and the variance actually. So sigma square is representing the variance of that distribution. So the two parameters that we are dealing with, actually I have mentioned here, sigma is a standard deviation, but we always write the square of the standard deviation. So this is a convention of writing down a normal random variable. Okay, so if you plot the curve of that probability density function, you can see that the maximum value of that function reaches when x equal to mu, because when x is mu, mu minus mu would be 0, then e to the power 0 comes out to be 1. So you are only dealing with the maximum value, which would be only depending upon the standard deviation of the distribution. So the maximum value you can easily calculate for that distribution if you just have a knowledge of standard deviation. And you can see this is a symmetric distribution. So it has certain features in this bell-shaped curve. First of all, this f of x is representing x is the value of the random variable. Small x in our notation is always representing the particular value of a random variable, and x is a random variable which is taken as a function which can take any value. And as we know, in order to be a valid PDF, the area under the curve of this distribution, so if you integrate this function from minus infinity to plus infinity, you always end up with 1. So we can see that the total area under the curve must comes out to be a 1. So if you integrate this expression from the limit minus infinity to plus infinity, you are always going to get 1. As we know, this mu value or the mean value is dividing the total area into two segments. So less than mu would be the area under the curve would be representing the 50% area, and greater than mu would be representing the 50% area. So if you add them, the total area would be 1. So this mathematical representation, and if you want to calculate particular probability for a given value of x, you just substitute the value in that function, you will be able to get the probability of that corresponding function. And the area under the curve for particular value, critical value, would be representing its cumulative density function. If you integrate it, the area under the curve would be representing the cumulative value, and we will see it in the later lectures. What do we see here? Once we are dealing with the parameters. So let's say you have a particular distribution where mean value is 5. So that is representing the center value, and if the distribution has a variance equal to 1, so 5 comma 1 would be the way by which we can represent this distribution. And let's say if mean value remains 5, but if you increase the variance, so once you increase the variance, the shape of the distribution changes in a manner that the spread of the distribution increases. So if the data has more variance, it means the spread of the data has increased. Or if if let's say the variance remains 1, but mean has been shifted from 5 to 15, so it means it is just a change of the location of the mean. So the central tendency of the data has been shifted, let's say from 5 to 15, it means 10 units to the right. And the shape of the, since the variance is 1, so it means it is representing the same distribution. So what we can conclude from this is higher the magnitude of variance, more the spread in the data, and the shape of the distribution would be much more spreaded. And if smaller the variance, let's say if we have a variance of 0.5, then we could have some less spread in the data. So the more the data would be towards the central tendency. And if we shift the mean, it means actually we are shifting the central tendency of the data. So these two parameters are representing this distribution. So for every value of mu and variance, there would be a particular shape of the curve. Okay, as we already know that the area under the curve is being represented under the curve of this PDF represents the probability. So let's say if me is its center value, and we integrate from mu plus 1 sigma to minus 1 sigma in the limits from minus 1 sigma to plus 1 sigma, so we would be representing the 68% of the area. So if any x is a random variable which lies in the interval between plus minus 1 sigma, then the area under the curves comes out to be 68.6827. So this would be the probability that your random variable would be lying in this interval. If we go to 2 sigma, then it means we are covering more spread in the data. So plus minus 2 sigma means your random variable could be greater than mu minus 2 sigma and less than mu plus 2 sigma. Then you are covering almost 95.45% of an area. So approximately we can say about 95% area is being covered between plus minus 2 sigma. Your random variable lies your any value between mu minus 2 sigma and mu plus 2 sigma. Similarly, if we go by 3 plus minus 3 sigma, so from mu this is 3 sigma to the right and minus 3 sigma to the left, then if the area under the curve would be around 99.7%. So these 1 sigma, 2 sigma and 3 sigma value, you must remember it. As you know, if you integrate it from minus infinity of x to plus infinity, then the total area comes out to be 1. And in the middle the area is divided into two parts, that is half. Okay. Let's say you have a typical distribution represented by 3 curves, and we have drawn all these curves with different colors. Let's say A represent a green color, B red color, and C some other color. The question for this particular problem is find out the mean of these distributions. So all these curves would be normally distributed, and how we can say that the normally distributed, because all these distributions have bell-shaped curve. But as we can see the from this scale on the horizontal, the A has a central value lies with -2. And the B, the central value lies with +3, and around 9 is the central value for distribution C. So these would be the typical values for their mean value for these distributions. So mean value for A would be -2, and for B would be 3, and for C would be 9. So it is where the maximum value of the curve lies, that would represent the mean value. So if you know, if you plot the distribution, you can easily work out the mean value, or if you know the mean value as well as the standard deviation, you can plot the curve. Okay, in the next part, let's say you have to answer which is the correct option for the standard deviation of the above distribution. So just take it a pause of this video and try to answer this second problem. As you see, A is a typical bell-shaped curve, and and B has a very less spread, C is more spreaded. So we can say that the correct option is C is more standard deviation than obviously they are not equal. A is not an option, and obviously A and C have not the same distribution, so B is not an option. So possible options could be C and D. So if you look at A is having more distribution than C, so this would not be correct. So we can say that C is highest, and then A, and the least is B. So D is the correct option. Okay, let's go into another problem. You have a distribution shown on this curve where mean value is the central tendency of the data, which is where the maximum of the curve lies, and if you know the maximum value, you can easily work out its corresponding standard deviation. Let's say the question is find the probability that your random variable lying between -2 sigma to plus sigma. So we are interested in area under the curve in that limit. As we know, these arrows are representing the area in all these segments. So you know it is 34%, 34%. So it would be 65% area between 1 sigma. And 95% in 2 sigma and 99.7% in 3 sigma. So we know all these numbers, so we can easily calculate by calculating the area under the curve. Let's say 0.135 is this, plus 2 sigma greater than -2 sigma is this, and then we need to add up these two things. So area under the curve from this limit to this limit would be the sum of the values of this plus this plus this. So 0.34 is twice, plus this value that would be representing. So 81.85 is the probability that your random variable would be lying in that limit. Let's say for next problem, find the probability that your random variable would be less than mu plus sigma. So you are interested in whatever is less than this. So take it a pause and try to answer such questions. You just need it because you know from this point up to this point, from -infinity to mu, the area is 0.5, and this one is 0.34. So 0.5 plus 0.34 would be area under the curve where x value is less than mu plus sigma. So 0.5 plus 0.343, that would be that area. If your problem is x is greater than mu plus 3 sigma, so any value which is greater than that, so you know this is 0.5, and then you end up of this, and the total is 1s, and 1 minus subtract to get this small area. So in problem 5, the area would be much smaller. So let's say you're up to this point, total area is this plus this plus this, and the whole thing is 0.5. So you note this whole area up to this point, and the total area is 1. So 1 minus this whole area would be this small area greater than mu plus 3 sigma, and this comes out to be 0.135%. So if you write any value which is greater than 3 mu, any value which is be greater than mu plus 3 sigma would be order of probability would be 27 parts out of 20,000 parts. So out of 20,000, 27 would be the probability that your random variable would be greater than that. So and once you put in the decimal place or in the fraction, it makes sense. If you write it like this, it has a different meaning that 0.135% is representing 27 parts out of 20,000 parts. So this is how you can represent or interpret the value of the probability. Okay, let's say now we have another problem which we will do it using the Minitab. I will just show you. Let's say this is the height of the adult American females. which is assumed that it is approximately normally distributed with a mean value of 162.2 and a standard deviation of 6.8. So we know that height of adult American female. So height can take any value, and it is a continuous random variable, and it is given in the problem that is normally distributed, and the parameters are given. So first thing you will always write about what is your random variable. And in your assignments as well as in your midterm, I have seen that you always missed this point. Whenever you are calculating probability, you must have to identify your random variable. So here x is a continuous random variable, which is actually representing the height of the adult American female as given in the problem. So this statement must you need to write before solving. So this would be always the first step. And second is in the shorter notation, you can say your random variable is normally distributed with the mean value as well as the variance. So variance would be square of the standard deviation. So always write, it is wrong to write mean and sigma, but it is always the convention to write mu and sigma square. So you always need to put like that. So we know that 6.8 is the standard deviation. Okay, and then your question is, what is the probability that you select a randomly selected adult female which would be greater than, taller than 170.5 centimeters? So what is that probability? So I will show you on this Minitab that we can calculate, and the corresponding probability would be representing 0.11. So we calculated using this Minitab, and I will show you just let's say if we have to calculate the value of a random variable if lies between certain interval from 150.5 to 170.5. So that would be the two values. So and 84.62% is this corresponding probability, and we will see it in this using the Minitab. Okay, let's see how we can do it in a Minitab. If we go to the calculate tab and calculating probability distribution, and you see the distribution, these are all continuous distributions and these are discrete distributions. So let's say I have to go to the normal distribution, just click on that normal distribution, and I'm interested in calculating the probability, let's say, and the parameter here for normal distribution shown is mean and standard deviation, and 162.2 I believe is your mean value, and 6.8 is your standard deviation. So and let's say your input constant is you want at 170.5, the probability at exact value of 1 point. If you do this at exact value of this 170.5, and let's see what result you are going to get. So at that would be the corresponding value of that function. So you know, when your x is 170.5, its corresponding value would be but it is not this, it is the corresponding value at that function. So f of x would be representing the probability density function, and so if I am interested in calculating the previous, if you look at the previous problem, I am interested in the probability not at what is this corresponding value, which is, if I look at here, it is something 0.02 and greater than 0.02 and less than 0.03. So what I am getting is 0.027, something is this value. So actually I am getting this corresponding value is 0.027, something like that. So that would be my f of x value, and I can see, if I plot it, I can see that value. But if I am interested in anything greater than 170.5, so I can calculate less than 170.5 and subtract it with that value. I will be able to calculate from that. For example, if I just go and calculating normal distribution, and this time I am calculating the cumulative probability, and my input value is 170.5, and I can see 0.889 is the area which is less than this, and greater than this would be 1 minus this value. So if you subtract 1 minus this, you will be able to get that probability. So instead of doing it, it is nice to do it on a probability distribution plot. For that, let's say I want to see the probability, view the probability, and I have let's say 162.2 is my mean, and 6.8 is my standard deviations, and my shaded area is, let's say, for right tail means greater than that. So my x value is, let's say, 170.5. So if I just click on that, I will be able to see this 0.111 is actually the corresponding probability when x is greater than 170.5. So 1 minus 0.111 would be 0.88, that value. And if you can see this function, you can see this mean is 162.2, and its corresponding value at that x is its corresponding value would be at x would be 0.027. That would be the value of that function. So this is how you can calculate the probability for using this Minitab. And let's say if I just do it for this other part where my distribution would be between certain range. Let's say I am in this range, some value of 170.5 to 150.5, let's say, and it is 150.5. This is actually 150.5 and 170.5. So this area is 0.8642. So let's say if my this is like this, so I can see 0.8462 is that area. I can just increase the font size, and can see that this would be the corresponding area between when your random variable would be lying between 150.5 and 170.5. So that is representing 84% of this area under the curve. So this is how one can calculate probability using this normal distribution. And by different graphs, you can see the variation of the different parameters. Let's say if you want to vary parameters, you can do that. Let's say my 162.2 is the mean, and 6.8 is my standard deviation. Let's say what I do is, instead of increasing the standard deviation or decreasing the standard deviation, let's say if my standard deviation is let's say 4, 6.8, let's say 8. So let's say if I just bring out those numbers for different values, and I want these graphs to be on the separate graphs or in separate panel of the same graph, or on separate graphs. So I can overlay it on the same graph. So let's say first I go with overlaid on the same graph. Then I can see that my mean was 162.8 for all different distributions. But if my standard deviation is 4, then I have some steeper curve, and if a standard deviation is 6.8, then it is much more spreaded curve, and if it is 8, then it is much more spreaded. So you can see how the standard deviation is changing the shape of the distribution. So all these things one can analyze through Minitab, the shape of the distribution. Okay, this is where I stop this lecture.